Good evening. I've told you that I have children, and some of my children were born in the 90s, and anyway, I've watched the movie Beauty and the Beast a few times, and so this is towards the end of the movie, and you've really learned to actually like the Beast, who's this guy, and really hate Gaston, who's this guy, and so it's a little satisfying to see him getting held by the neck here, even though it's a bit violent for kids. But anyway, it's a great scene. But what's nice is that the Disney animators have had the Beast grab onto this gargoyle over here so that he can be in static equilibrium. Because obviously, if you're holding Gaston off like that, there's going to be, well, two things. There's going to be the downward force of gravity on the Beast, which to me looks like it's off the edge a little bit already. But also you got Gaston over here, who's pulling way down on his hand, and there's going to be quite a large torque from here because of this large distance between the rotation axis, which I assume is his foot, and this downward force of Gaston's neck on his hand there. So he's got so these are both counterclockwise positive torques. So you're going to need a clockwise negative torque from the force of the gargoyle. But don't forget, to be in static equilibrium, you also have to balance the x component of the forces. So I think there's also, he must be pushing actually this way with his foot and then pulling with the, anyway, so let's see. The other question I wanted to do, just a quick little survey about those scratch cards. What we have done in the past is use a normal bubble sheet for our multiple choice questions. I'm going to give you a bunch of multiple choice questions on the final exam and also in Physics 132 as time goes on. But the scratch cards are kind of a new thing. They're a bit fancy, and they have pros and cons. So why don't you just discuss among yourselves a little bit which you prefer, and click in. So I am going to stop this. Thank you very much. I did this morning in Con Hall, and I kind of got something I think is pretty similar. I'm going to stop this. But the idea, I think actually what happens with these is that the people who kind of like it, and the people who hate it really, really hate it. And want scratch cards to die, and so there's kind of like, even though it's sort of 80%, 20%, those 20% have a very, I think, a kind of a valid issue with it, which is just that if you're trying to manage anxiety, I think during a test, which I always had to do when I was a student, if you're scratching off these things, being told you're wrong, you're losing points, it just actually makes you get even more worked up and upset. And so what I actually witnessed some students doing was waiting until the last 5 minutes of the midterm to scratch anything on their card. They were just circling the answers and going through the same way they would with a bubble sheet and going, okay, I got this, I got there, they're feeling good. And then they sat and wait, and when there's 5 minutes left, okay, now I'm scratching. And they wait and they scratch through. And if it was wrong, they were like, and then scratch the other ones. Because I think these students probably know themselves that they're going to get all worked up and anxious. And when you're feeling upset, you can't think about physics very well. So come on in if you're new. There's lots and lots of free seats. Please, if people are coming late, just allow them to squeeze in. There's lots of room there. Okay. Does anybody have any questions? I guess there were some questions from before or on the Learning Catalyst about the final exam. Short story with the final exam. We will talk a lot more about it, but it'll be twice as long. It's 3 hours. We're going to give, instead of 12 multiple choice questions, there will be 24 multiple choice questions. Instead of one long answer to get right out, there will be two. And it's as simple as that. And it's 7 to 10 p.m. on December 11th, I think. Any questions? Yes, question. I can't hear you, sorry. Still nothing. Either yell much louder or people are going to have to let you speak. Are we still using scratch cards? So if people could allow the student to ask a question, which is a very good question. I like a little back and forth, but sometimes we need to have the airspace. Yeah, I think it's going to be scratch cards. I don't see why not. They're sort of working, for us. Again, we're not quite sure what's going to happen in Physics 132, but it's like I said, the scratch cards are coming. If you got an issue with them, try to make the best of it, I think. And there is even a way, I guess, you could just choose which one you're going to scratch, and then just cover your eyes, scratch it. You wouldn't get any second chances, but just go down that way. If you don't hit the star, you don't even want to know. You could do that. I wouldn't do that. Any other questions before I get on to static equilibrium problems? Anything anybody want to bring up? Okay. Let's talk about these three equations down here. So this is static equilibrium problems. We're finishing up chapter 8, and I'll do a couple of examples, but it's always the same. You got an object, if it's not accelerating, and if it's not rotating, if it's not moving, then it has to be in static equilibrium. It means there must be no net force on it, either in x or y direction, or z. No one ever talks about z, but anyway, that's also true. And also there has to be no net torque. So strategy is you draw an extended free body diagram that shows not just those forces, same way you did with a regular sort of force diagram or free body diagram, but also where they attach. You set up your x and y axes. You must choose a rotation axis, because if it's not rotating, you can choose that anywhere you want, and it still works. And then each force has an x, y component and a torque. So you just sum them all up, and these are the equations you use. So I think I'm going to, well actually, let's do a quick, another learning catalytics question. I'll just send this to you, and then we'll do some examples. It's more of a conceptual one. An object could be in static equilibrium when A, only one force is acting on it, B, two or more forces acting on it, or C, only one torque is acting on it. Feel free to discuss. I'll give you 1 minute. 2, 1. Okay, good. So the answer that I was looking for is B, like that. So basically, if there's only one force acting on an object, then that one force is the net force. I guess an example of that would be a projectile, right? There's only one force acting on a projectile, and that's gravity, and so it's accelerating all the time. It can't be in equilibrium if there's only one force. And similarly, if there's only one torque, then that torque is the net torque. And if it's not zero, then the thing is going to be rotating around. So let me see if I can, he says it's on the doc cam. Yeah. So let's see if you can read that. There's two problems I'm going to show you. Zoom in a little bit. And they're kind of the standard canonical problems that you always get in static equilibrium. And I call them the ladder and the sign. There's either usually a ladder leaning against the wall, or there's a sign that's hanging off a wall with some cable. So let's do both of those. And so you've got a 3-meter-long ladder. It leans against a frictionless wall. So this wall has a normal force N2, but doesn't have static friction. At an angle of 60 degrees is this angle down here. It says, what is the minimum value of mu sub s, the coefficient of static friction with the ground that prevents the ladder from slipping? So it's important. You've got a frictionless wall, but a friction-y ground. If they were both frictionless, I think that ladder would go woo and slip every time, right? So you need some friction, and it's down here. So part of my sketch and translate, I'm going to say that this is rigid body, static equilibrium, something like that. It's good to write down that stuff. You should say somewhere here, let's define the y-axis to be up in that direction, the x-axis to be towards the right. Let's define the rotation axis. We can put it anywhere we want, as a matter of fact, and the torque around any point is 0. But it's good to be smart about this. What I like to do is put it where one of the forces is, so that force has a 0 torque. because if the force is acting on right at the rotation axis or through it, then it doesn't have a torque. And it's usually good if you put it on forces you don't care too much about. But I think, or one where this point has two forces, so if I put the rotation axis there, then I only have to do two torques. So that's what I'm going to do. Foot of ladder. See if it works. If you really get stuck, then you can always go back and define a different rotation axis and try it that way. Okay, so the simplifying diagram is down here. Let's, well, it's a rectangle, so that's easy. Let's draw it again. And we just draw those forces. Like you've kind of already drawn it there, but it's good to draw it again. So you've got N2, N1, Fs, and then I'm going to, the other thing that it says here is something about, oh yeah, it says center of mass. I guess it's uniform. So we assume the center of mass is, I guess, L/2 up. And that's going to be mL times g. Can you read that? Mass of the ladder times g is the gravity force. And what we're trying to find is the minimum mu sub s will be for when the thing is just about to slip. So generally with these physics problems, when you're dealing with static friction, there is no equation for static friction because it's like normal force or tension. It is whatever it is to balance it. Unless somewhere it tells you that or implies that the thing is just about to slip. If it's just about to slip, then you know that Fs equals Fs max. And so then you have an equation for that. Do you remember it? Fs is just mu sub s times the normal force. But unfortunately, there's two normal forces, so I have to decide which one to use. Anybody got an idea? N1? Let's use N1. N2's up at the wall, it doesn't matter. What matters is N1. So that's a good equation. It's probably going to end up being important, so let's circle it and push the whole thing off to the left. You got the idea? And now let's finish this thing. So what else are we going to do? So the basic thing, I always just set it up somehow. You know that the sum of the x forces equals 0, the sum of the y forces equals 0, and the sum of the torques equals 0. So just do those three equations and you can solve for up to three unknowns. And we got another equation down here. We'll call this equation 1 or something like that. We may use that one. Okay, so x forces. Let's see, there's only two of them, I think. There's the N2 and then the Fs. Okay, so this implies that N2 equals F sub s. So that's an equation right there. We call that the second equation. That might be useful. What else? Y forces equals 0. So we've got the gravity pulling it down. So it's a negative mass of the ladder times g. And we've got the normal force pressing up. That is equal to 0. That means that N1 is equal to mL times g. That's a good equation. I shall call that equation 3, in case we need to use it later. And then what else do we got? Okay, yeah, so the torques one is the one's a little harder. So these two down here don't matter. They don't produce a torque. You have to get a torque from the gravity and a torque from the normal force. So let's start with the normal force. So it's N2 times the distance, which is L, the length of the ladder, times the angle between that L and that force. So I think it's 60 degrees. So it's sine of 60 degrees. And is it positive or negative? If it's going to be, normal force is going to push to the right, the rotation axis down there, it's going to go clockwise, so it's negative. Good? That's that first torque. Next torque is going to be positive because it's going to twist it to the down and counterclockwise. There's the mass of the ladder times g. There's half that distance, L/2. And then we have to find this angle right here, which I think is 30 degrees. So sine of 30. So let's call that equation 4. Did it fit on my screen? Yeah, just barely. So this is kind of it. What we have is, I think, actually 4 equations, because if you count that first one, and 4 unknowns. The unknowns are going to be n1, n2, f sub s, and mu sub s. So we just need to solve for this. Find that one. By just eliminating all the rest of the things. We're just going to try to do it. Okay? It's sort of algebra from this point on. So far, what we've done is the tricky part. That's all the physicsy stuff. Now let's do the math stuff. All right, so it's equation solving. What do we have here? So I think that if you take equation 4, that implies that mu sub s, which is what we're after, is equal to the friction force divided by n1. And then if we want to get rid of that n1 on the bottom, I guess we can use equation 3, which says that mu sub s is equal to f sub s over mlg. Those are some knowns, so that's good. And then don't forget from equation 2, we can plug in for fs, you get mu sub s is equal to n2 divided by m sub l times g. See? I sort of used a bunch of equations, so I'm down to that. And now the n2 is going to come from equation 4. Is that, sorry, that's equation 1. Equation 4 is the torque one, and that's going to be that n2 times L times sine of 60 degrees is equal to ml times g times L over 2 times sine 30. I think the capital L's, the length of the ladder, cancels out. And I end up with n2 is equal to ml times g times sine 30 divided by 2 times sine of 60. And these are degrees, not radians. So now I can take this whole thing and plug it into there. So I had a normal force on the top and normal force on the bottom. I end up with mu sub s equals ml times g times sine of 30 degrees divided by ml times g times 2 times sine of 60 degrees. Wow, the mass of the ladder just canceled out. And luckily, all the things that we have left are dimensionless, and the coefficient of friction is dimensionless, so it's good. So it's just equal to sine 30 degrees divided by 2 times sine of 60 degrees. I plugged that into my calculator, and I got 0.29. So that's the solution. And if I was to evaluate, I might say that sine 60 degrees is in denominator. Okay, and so this angle, if 60 is increased, this minimum, mu sub s minimum, will decrease. And it slips if the real coefficient of friction, I guess, is less than that. So if you've got a lower minimum, and you have to be less than that to slip, then it's harder to slip. Meaning that if you have a ladder leaning against the wall, if you increase this angle and get it closer to the wall, it's less likely to slip. And conversely, you put it further up from the wall, it's more likely to fall down. Anyway, I was talking to Brian Wilson, and he said anything that you put in the evaluate stuff that's just sort of intelligent and says something about what you just did is good enough for that point. So I got to get better at doing evaluate. Any questions about that one? Yep. Nope. Sorry, it's not your hand. Okay, so I told you there's two things. The ladder against the wall. The other one is the hanging sign. Let's do the hanging sign. Can't quite see him. Sorry. You see him? Okay. So sometimes it's a sign, sometimes it's a beam. This is one with a construction worker guy sitting on it. Uniform steel beam of length L and mass M1. It says uniform, so that right there indicates to me that the center of mass is in the middle, L/2, of the beam. Is attached via a hinge to the side of the building. And then the beam is supported by a cable with some tension that's attached to the end of the beam, and there's an angle theta. Through the hinge, the wall exerts some unknown force F, kind of like that, I guess, F. And then the workman of mass M2 is eating his lunch a distance D from the building. So it says find tension in the cable and find F sub x, the x component of the force exerted by the wall on the beam. So this is going to be split into two components. Kind of like the normal force, I guess, would be F, negative Fx or something, and then the friction or something. So I probably should have done this before. The system was the ladder. For this one, the system, let's make sure we know, is the beam. System is the beam. And then all the forces on the beam are external forces in the beam. So this is, the next one I'm going to do is this reasoning. The workman is involved. And the workman is pushing on the beam because he's sitting on it. And he's pushing downward on the beam. I hope we get that. But the way I go through this in my physicsy mind is I say, okay, it's a three-step process. First, the earth has a gravity force that grabs the worker and is pulling him down. Step two is that he doesn't go down because the beam is pushing up on his bum. That's step two. And then step three is because the equal and opposite forces, by Newton's third law, his bum is pushing down on the beam. But anyway, in all cases, those forces are the mass of the worker times g. So I'm putting this up here. The workman pushes somehow down on the beam with F is equal to the mass, his mass, which is M2 times g. Is that fair enough? I'm going to put that as an external force on my force diagram. So let's draw it. There's T, there's theta, there's M2, times G, and there's M1 times G, and there's these distances, which is this is the distance L/2, and this is the distance D. And they're both, these angles is 90 degrees, which is lucky because the sine of 90 degrees is 1, so that's going to make things a little easier. Oh yeah, and there's one more force. So the other force is that force of the hinge, which I haven't drawn yet. And it might be on a diagonal, so I think what I'm just going to do is split it into its components and treat those torques differently, rather than do some crazy, I don't know the angle or anything, so let's just call this Fx, which is what we're trying to find actually, and Fy. So I've ended up with 1, 2, 3, 4, 5 forces. And again, I'll scan that in, but that's my basic idea. And I'm not going to go through and do this whole problem, but I'll do the next step anyway, which is, what do? You always do the same thing, which is the forces in the Fx equals 0. The forces in the Fy, all the sum is equal to 0, and the sum of all the torques is equal to 0. And what we hope is that these ones give us enough so we don't have to do the torques, because we hate doing torques, but it usually doesn't work that way. So I think this tension is going to have a positive T cos theta probably. And then this x plus Fx equals 0. But we don't know tension, so that's not really helpful. The y components is going to be, there's going to be a T sine theta. And then minus those gravities, M1g minus M2g, and then plus F sub y equals 0 again. Okay, so we're down to torques now. The torques are going to be Uh-oh, I can't do the torques. Do you know why? Forgot to define the rotation axis. Let's do rotation axis. Equals the hinge. Maybe that was obvious, but I think that should be in your assumptions. Okay, so now that we've got that, I've got the tension is going to produce clockwise torque, so there's going to be a negative sign, tension times L times just sine theta. And the sine theta here comes from that equation for torque. The force times the distance times the angle between the force and that radius line to the rotation axis. Make sense? It's a different sine theta than those other ones for the x components where we're just finding components. Anyway, and then we've got plus m1 times g times L over 2 times the sine of 90 degrees, running out of room here, plus m2 times g times d times the sine of 90 degrees. And the sine of 90 degrees equals 1. So basically these just are all torques, so what we end up with here is something like T times L times sine theta equals m1 times g times L over 2 plus m2 times g times d. Anyway, then there's a bunch of algebra. Sort of what we've done here is we've done the hard stuff, which is the physics. We're drawing your diagrams and setting up these equations, and then the easy stuff is solving you got 3 equations you can solve for 3 unknowns. Questions about that? Yes, question?
Oh, wait.
You good?
The answer is usually positive because the rotation axis is
Yeah, what I think is that the rotation axis is here, so both those gravities are going to pull it counterclockwise. Yes?
So we talk about assumptions for those torque axis.
I beg your pardon?
Do we write assumptions for this torque axis?
Yeah, I guess assumptions are, I kind of put it something about the system is the beam, I guess that's an assumption, and maybe rotation axis, that's more like a definition, but sometimes people say that it's static equilibrium, that's an assumption. It's pretty simple. Everyone's always stressed about what are the assumptions and what are the evaluations. Yes?
So for the angle of the torque, what do we just assume that it is? The angle of the torque?
That theta angle, that one would be given to you in a question. It's one of the knowns, I guess. You don't solve for theta in this question. Good question. Okay. All right. What's next here? So, we're moving on to the very last section of chapter 8, which is about, it's about stability, equilibrium, and tipping objects. So, you have probably observed that it's easier to balance if you stand sideways to the motion of the train on your subway and kind of keep your legs sort of far apart. And then you don't have to grab onto anything. And by assuming the stance, you increase your area of support. And the idea with the area of support is that if you take your center of mass and then draw a line straight down from that, then it has to be between the 2 most outer limits of your area of support. And if that's true, then it doesn't fall over. And I was just looking at this empty bottle of wine, which, I don't know, before the midterm this might have been full, but it's gone now. So it's another one of my party tricks. I asked Pius, I walk around with Pius, and there's these storerooms all over this building, which is 50 years old, just filled with all kinds of stuff. And so you have to get it just right. If you push the bottle too far in, then the thing tips that way, and if you pull it out too far, then it tips that way. But the area of support is a very small area, which is why this looks kind of fun. And if you get the center of mass of the wood plus the bottle directly over that, then the whole thing doesn't tip over. So that's what that's about. That's my party trick of the day. What else do we got here? Tower of Pisa, same sort of thing. The reason the Leaning Tower of Pisa doesn't ever fall over is because the center of gravity is still over the area of support, which is the bottom of that tower. If it got too far, that thing would tip. It's called stable equilibrium as well. And the stable means that if you perturb it, it accelerates back towards where it wants to be. And then unstable is when, if you perturb it, it accelerates away. I think this one's unstable, yeah. That's so small that it's unstable. Okay, oop. Okay. Let's put it, I think I've just shown some answers here, but let's go to, I'm going to send you Learning Catalytics. And I'm going to turn this off for 1 sec. There it is. The idea with this is that you've loaded up a truck with a whole bunch of boxes, and they could be shoved over to the side or way up to the top, but somehow you know the center of mass of each of these trucks, including everything that's in them and the trucks, to be at these 3 spots. So considering each of these trucks separately, are they going to tip over or not tip over? Which one tips is the question? A, B, or C? Going twice. Yeah, so I could see some people trying to judge this, but I think, because certainly C, if you just go straight down from C, it's within the base of support, so it doesn't fall. If you go straight down from B, I think you're still okay. But if you go straight down from A, well, now there's nothing supporting you there. So the gravitational torque in this object around this rotational axis, if you choose that to be the rotational axis, will be enough to tip it. Great, got another question for you. And this is similar to something that came up on the homeworks. So take a look at this. Stand at the front. A refrigerator is 2 meters high, 1.4 meters wide, and it's 1 meter deep. It doesn't say that in this, but it is in the homework. On a flat floor, by what maximum angle can it tip sideways and still not fall over on its side? So this is a bit of a different question, but it's useful to do these. I think it's basically just a geometry question, but let me try to draw it. So my initial drawing looks something like, it starts like this on the floor. It's got 2 meters high and 1.4 meters wide. It's a very short, stubby fridge. And I'm going to assume, I guess, let's put an assumption here, that the center of mass is at the geometric center, which isn't necessarily obvious, but it's not stated anywhere, so I think I just have to assume that. So like 1 meter up and stuff. So like 1 meter and 0.7 meters, something like that. So now I'm going to, like just about to tip, will be something like this. There's the floor. And then the center of mass is right over the tippy point. Does that make sense? And then I have to draw everything. I think there's going to be a 1 meter here and a 0.7 meters here. And this is the angle that we're trying to find is theta. And after that, then it's going to go right over. But this will be the point where it just kind of balances. Less than that, it'll fall back down and stand up. More than that, it'll tip over and fall over on somebody. So now it's just, I have to do this triangle. So let's draw it again. right angle here. This is theta. So this angle, I think, is 90 minus theta. Right there. And then this angle up here must be theta. Right? And then this is 1 meter, and this is 0.7 meters. Sorry. So I think it's going to be that tan of theta is going to be 0.7 divided by 1, opposite over adjacent. And so then theta just equals tan to the minus 1 of 0.7 over 1. And so once again, I can try to do that on my calculator. So the tan thingy is above the direct press shift, tan to the minus 1, and then 0.7 divided by 1. And I got 35 degrees. Something like that. Okay? Questions about that one? So we got a little time for a game called Stability Jeopardy. I don't know if you guys are in the mood to play a little Jeopardy. The idea is that I give you the answer, and you have to guess what the question is. And this one, I didn't really teach it, so you're going to have to kind of bear with me or get out your Google or something but just try your best. It gets easier. The first one's the hardest question, so they didn't like this much this morning. But I'll show you what I mean. Oops. Okay, so we'll do a little bit of an idea. The stability of equilibrium is an idea where an equilibrium is stable if a slight disturbance from equilibrium results in forces that tend to restore the equilibrium. It accelerates back towards equilibrium. And an equilibrium is unstable if a slight disturbance causes the system to accelerate away from the original equilibrium. So that's instability and stability. Like a cone on its base, you give it a nudge, it's going to accelerate back to be standing up. A cone the other way, you're going to give it a tip and it's unstable. And a way that a lot of people analyze stability is they make a plot actually of potential energy versus distance. And so you kind of, if you show like a bull, for example, and you have something at the bottom of the bowl, you push it this way, the potential energy goes up, and so it wants to rock back down to the bottom of the bowl. And that's a stable equilibrium. Follow me? Ready for first question? There are 4 classes of equilibrium based on these graphs. So that's your preamble. I'm going to deliver the first question here. So I'm going to ask 4 questions based on these 4 types. So this is the hardest one, like I said. Let's see if I can eliminate. What I need is that Jeopardy song. Ding, 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 ding. This might be a bit of guesswork, but I'd say these get a little easier. So this is a situation where the ball is in equilibrium because it's on a flat surface. So there's no net force on the ball at that position. But if you give it a little nudge to the left, it will go to some velocity and will continue at that velocity and just generally go. It won't accelerate back and it won't accelerate away from its equilibrium position, or it might just find a new equilibrium position. We just call this, it is neutrally stable, I guess. It doesn't want to rush away. Neutral. Neutral stability is what it's, so, okay. Right. Again, I'll give you 1 minute. So this, again, it's not going anywhere because there's no net force on it. But in this case, you perturb the ball a little bit, and it rushes back towards equilibrium. And what's interesting about stable equilibrium is that when the ball returns to its original position, it almost always overshoots at equilibrium and goes the other way, and then turns around. And so what will happen is it'll oscillate around a stable equilibrium. So, and this is the entire subject of Chapter 10, which is a simple harmonic motion and oscillations around equilibrium. Okay. Next one. Good. Minute. Okay, so once again, it's in equilibrium. If it stays exactly there, it's not going to go anywhere. But if you perturb it at all, then it will accelerate away from equilibrium. And so that's what's just called unstable equilibrium. And then last one. Yeah, missed that. Okay, so let me just finish off by talking about metastability. And so this is sort of from the wiki page. So what this means is that if you give a small perturbation from equilibrium, then a metastable state will return back to its original position and oscillate. If you give a larger perturbation, then it can become unstable and rush away. And so some examples of metastability. One is if you have a ball that rolls down a hill and it ends up in a little hollow on the slope, if you can imagine that, and it stays there. If you perturb it a little bit, it stays in the hollow. If you perturb it a lot and it goes over the edge, it could continue rolling down the hill. It's metastability. Bowling pins have this effect. If you've ever gone bowling and you just hit the pin a little bit, you might see it sort of wobbling around, wobble, wobble, but it doesn't completely fall over. That's metastability. You've given it a little nudge and it's gotten back to straight up. If you give it too much of a nudge, it goes right over. In chemistry, we have something called isomerization, so it's possible to have two different chemicals that have the exact same chemical formula. So the same kinds of atoms in both molecules, but they're arranged a little differently. And that arrangement has some energy associated with it. Now, the only way you can have a stable molecule is if you are in some sort of stable valley of potential energy. So if you perturb these higher energy isomers a little bit, they return and they do form a stable molecule. But if you perturb them too much, then they release energy and go to their ground state and change their chemical configuration. So that's an example of metastability in chemistry. Anyway, good night, and see you next Monday.